essentially, I rushed through a little bit of the proof at the end, so I want to redo it at least once, just because the idea is cool. I will be clear, if you don't fully understand this at the end, that's not a problem. We're going to sort of immediately jump into other things where you'll need to maybe know as a statement, but you won't need to know the proofs. And I believe, we'll see if I can get away with it. Today might be the last time I have to mention things like Martingale Convergence and optional stopping time. I'm hoping to move away from the quite as heavy probability. So, yeah, general plan of the day. I'm going to start by just recapping yesterday, talking a little bit more about the relationship between groups' theoretic properties and what we said, and then we're going to pivot and start to actually define the Poisson boundary in its fundamental things and go through a few examples. All right. Right, so I'm not going to cover all the details of yesterday, but I'm going to focus on the main part, which is the statement. You have a non-degenerate measure, which again, reminder, just means it generates a group as a semigroup. Then GX trivially, and using a little bit of probability, you can reduce down to the case where G is actually in the center of G. So we're going to focus on that case. That's sort of where the core interesting idea comes in. So we have an element G and G, and we're even going to assume that G is in the support. Again, there's a drop of tech, like you have to take a convolutional power to do this, but it's really not a painful assumption. It doesn't actually reduce the generality at all. So you have a measure mu with G given some non-trivial support. And now we consider the space of mu harmonic functions bounded between 0 and 1. Again, it's a compact convex space. So if there exists a function which is not fixed by G, there's going to be an extremal such function, right? Again, because the point is convex hulls are going to preserve this. So then we can just apply our formula for decomposing it as a harmonic function. And I should be clear here, I think I gave an incorrect definition of multiplication last time. In general, when you move f of g of x, you have to write a g inverse on the other side. It's a general annoying thing that happens whenever your group is non-commutative. It's right, just this shows up all the time in dynamics and probability theory. And I think many other people, when you're just writing it down without thinking a lot, will often make a mistake. There's often just a formal flipping that needs to go on. Right? So we have f of xg is f equal to f of gx, which just definitionally is going to be equal to g inverse of f of x. Right? So now we just look at this first term, and it's some fairly complicated thing. And again, it's a sum of things, all of whom are bounded between 0 and something. And if I just sum up all their upper bounds, it's going to be less than 1 minus mu of g. So I can rescale by 1 mu minus mu of g, and I'm going to get something that's also still bounded above by 1. And again, they're all already bounded below by 0, the things I'm summing up with. The thing I get is bounded below by 0. But here's the interesting thing. And here's something which is a little bit more subtle. Not the subtlest, but more subtle than in the case where, the entire group is abelian. In order to see that this thing is harmonic, these parts now are not necessarily harmonic. In general, something of the form, like if I take f and I take a function of the form f of xh, that's not a harmonic function in general, even if f is harmonic. So in order to, f of hx, on the other hand, is. So, right, we have f of xg, and the reason we know this is harmonic is because it's equal to f of gx. And so this thing is the sum of a bunch of non-harmonic functions, but it's also a difference between two harmonic functions, namely, f and f prime. Sorry, f and g inverse of f. So what that means is that f is going to be a convex combination of two things, both of which belong to C. And thus, since f is extremal, f is equal to g inverse of f. If there are any questions about this proof, please ask now, just because we're going to be moving on to different things. And so if you want any last chance, just let me know.
Okay, I will. What was the statement? I'm sorry.
No, of course. I should have included this on the slide. We're proving that if you have a central element of G, we're trying to prove that every bounded harmonic function, which I guess if you have mu with G as a support, G is going to act trivially. Right? So the point here is that anything in the center acts trivially with this mild assumption on the measure. And then, again, sort of using some standard manipulations, you can improve this to the case where your element isn't center, but just has a finite conjugacy class. And your original measure doesn't necessarily have to have it in the support.
Okay.
All right. So we have this lemma. We have this lemma about sort of something acting on trivially. Or something, these things with finite conjugacy class act trivially. So in general, this makes me ask, and a lot of us ask, okay, what about the things that always act trivially? So if you have your space of bounded G mu harmonic functions, right, there's some elements which maybe are going to act trivially on all of them. Right? So you have this G action on the thing just by, translating your functions. And there's some kernel H of it. And the point is, well, you might as well have modded out by H at the beginning, right? It does nothing. There's a very canonical thing. If I have a mu harmonic function, I can just push it forward to a mu G mod H harmonic function on G mod H, right? So I just take the thing, my measure on G, I mod out by H, I get a measure on G mod H, and then whatever was my original G function is now mu G, like G harmonic function, is now a G mod H harmonic function.
Sorry, Josh, there's a question in the chat. For a general locally compact group, is the measure mu asked to be absolutely continuous with respect to harm measure?
Exactly. That's the assumption we usually put on in the locally compact case. So what can we say about this kernel? Right? Because again, in some sense, we just showed that it doesn't really matter. Well, just by the above lemma immediately, it includes every element with a finite conjugacy class. But actually, it's somehow way stronger than that. Right? If we mod out by H, every element of H acts trivially. That means in G mod H, everything is acting non-trivially on at least one harmonic function. Thus, every element other than the identity must have an infinite conjugacy class, right? Otherwise, it would still be acting trivially on all these functions. Thus, G mod H must satisfy the infinite conjugacy class property. What is the infinite conjugacy class property? Well, it's exactly what I just said. Every element other than the identity needs to have an infinite conjugacy class. So, right? So in other words, we just proved that if a group has any non-trivial bounded harmonic functions, or any non-constant trivial harmonic functions, you automatically get that the group has an ICC quotient, namely the elements which act non-trivially on any of these functions. And moreover, just so, well, and I'm going to talk a little bit more along these veins in a little bit, sort of just the general structure here. So given a general group G, we denote by FC of G as a subset of G consisting of elements with finite conjugacy class. So this is called the finite conjugacy class center, or the FC center is the word I like. And from the word FC center, you might think it's analogous to the center, and you'd be right. The FC center, the way I always think about it is, oh, sort of from an infinite group's perspective, this is what you want the center to be. It's a little bit more complicated. It doesn't work in all things, but for lots of applications where you don't really care about finite index, FC center is the right notion rather than center per se. And no, the FC center is just always a characteristic, in particular normal, subgroup of G. Right? If I can tell you G, every automorphism of G is going to preserve the FC center. But we're going to do something a little bit in analogy with nilpotence here. Right? So when nilpotence, right, it doesn't automatically follow that when you mod out by the center, you don't get any more elements in the center. Sometimes when you mod out by the center, you get new things. And if you keep on doing that, and then at some finite stage you end, you have your nilpotent group. So we're going to define something like these things, these FC alpha centers. And we're going to have to include an ordinal. You actually already have to do this in the regular center case. So what are we going to do? Well, the first FC center is just going to be the FC center. And then the second, or I guess I should start with the zeroth. The zeroth is just going to be the identity. The first one is going to be the FC center. And then the second one, I'm going to mod out by the FC center. And now I'm going to get new elements. So I'm going to get a new FC center. And now I want to mod out by them as well. So that's going to give me some new things to mod out by. But I want these all to be sort of elements of my original group, so I'm going to take the preimage. And then the third, I'm going to mod out by this, second FC center. I'm going to get a new FC center, and I'm going to take the preimage of that. And so on and so forth. So this is an increasing sequence of groups. But what do I do at limit ordinals? Well, I have this increasing sequence of groups. I'm just going to take the union of all of them. But it might turn out that even after I've taken the union of all of them, there are new elements that even though they previously weren't in any of these FC centers, when you've modded out by all of this, become part of an FC center. But this is a sequence of increasing groups, right? It's getting bigger and bigger and bigger. So eventually, it's going to stabilize, right? You can't keep on adding elements indefinitely, right? For some ordinal, it's just the ordinal would be too big. So this group eventually stabilizes something called the hyper FC center of G, right? So it's sort of built up by all these FC centers. But there's another interpretation, which I sometimes like more, right? It depends on what you feel like, whether you like the sort of recursive ordinal definition. But when you mod out by this hyper FC center, well, you get an ICC group. Why? Well, you can't have anything that has a finite conjugacy class anymore. Otherwise, you could have extended your tower even larger. So, and similarly, any quotient to an ICC group, the kernel has to include the entire FC center. Why is that? Well, suppose it didn't include the entire FC center. Then there would be some element with smallest ordinal, which belongs to a smallest ordinal class, which isn't sent to the identity. And because it's the smallest one, you've modded out by everything below it. So that would be in the FC center. So in other words, every map, right? So it's mapped to the universal ICC quotient. There's sort of a largest ICC quotient. You can write a little diagram with a universal property if you want. And it's just the kernel of this map. So a group is hyper FC central if it's its own hyper FC center. And I want to talk to you now about, and a sort of important analogy is not even the right word, but my claim is that this is going to be the right generalization. And there's actually many contexts, or well, at least two, but I believe many, where this is true.
Sorry, can I ask a very silly question? So is the trivial group is ICC, right?
The trivial group is trivially ICC.
Okay.
When I say ICC, I'm usually thinking of a non-trivial group. Mm-hmm. Right? Okay. I mean, like ICC often means implicitly infinite ICC, right? Mm-hmm. What you do is a trivial case.
But for example, in the universal ICC quotient of an abelian group
is exactly the universal quotient of an abelian group is a trivial group.
Okay.
Because there are no non-trivial ICC quotients. Exactly. Mm-hmm. So I'm going to argue that a hyper FC central group is sort of the right generalization of virtually nilpotent group. And the following theorem is going to give me a very compelling reason why this isn't at least obviously wrong. If I look at finitely generated groups, virtual nilpotents and hyper FC centrality are the same thing. This is a theorem of de Guida MacLean. One direction is actually pretty easy, right? If you're virtually nilpotent, right, that means you have a nilpotent group of finite index. You can just check, right? Taking this sort of finite extension isn't going to increase it's going to turn central elements, and maybe they will start to have, finite conjugacy classes, but anything which had a finite conjugacy class is only going to be mapped to a larger finite conjugacy class. Finites aren't going to go to infinites. But so one direction of this is actually pretty easy. And I'll include it on the exercise sheet. People should feel free to attempt it. The other direction is like surprisingly hard. When I learned about this, right, it's in two fairly obscure papers from the 1950s, and you have to put together both papers in order to get the result, because they didn't have the notion of virtual at the time. That was just not a word they used. So the language is a little bit antiquated, and the proof, I have some short survey paper where we cover it. It's not so long, it's only 5 or 6 pages, but there's a number of ideas. It's a very clever argument. So, right, one sort of philosophical thing I want you to take away is if something sort of behaves well with respect to finite index extensions and is true for nilpotent things in the finitely generated case, in the infinite generated case, look at hyper FC central. That's somehow the right generalization. And similarly, groups that are not virtually nilpotent. So these are groups of, by Gromov's theorem, super polynomial growth. These are analogous to groups with an ICC quotient. So there's a bit of an analogy there. All right. So, yeah, I guess that's the end of the pure sort of group theory and these things. I'm about to define the Poisson boundary, but if there's any questions people have on that material, please let me know. So I'm going to give just a little bit of heuristics about the Poisson boundary right now, just sort of the big picture before we actually get to defining it. So we want to better understand the space of, I say harmonic functions, I mean bounded harmonic functions on a group. All right, here's a very general idea that we're going to make very precise. Random walks and harmonic functions seem really close, right? You sort of use a random walk, and then it stays the same value as a harmonic function. why don't we just understand random walks instead? Like, can we connect the two? Can we say they're basically the same? And so what we're going to do is we're going to take the connection is a little weird, and it was a brilliant idea. This is due to Furstenberg, and honestly, if you look at his Abel laureate citations, this is one of 3 things that got him the Abel Prize. So this was considered a brilliant idea at the time, and at least to me, I look at it and I'm like, wow, it's really beautiful. So we're going to find a measure space related to random walks. I say which is very closely related to Poisson boundary, but what I mean is it's very closely related to bounded harmonic functions. And again, it's right. So let me actually get to the definition now. Right, so let's say I have a group G and a probability measure mu. Right? I want to look at the space of all paths on G with a random walk measure on that. Just to recall, right, what that means is I have G1, G1, G2, G1, G2, G3, G1, G2, G3, G4, and so on and so forth. And then I want to say the probability that in my first n steps I do G1, then G1, G2, G1, G2, G3. It's just the product of all these step probabilities multiplied together. Right, so this is a random walk starting at the identity. I'm going to define 2 paths to be tail equivalent if there's an M and an N, so that starting at M and N, they agree. So I'm going to try and draw a little bit of a picture here. Right, so maybe, right, one of my sequences is this one, right? Just, I guess I should say on Z. And maybe the other one right? Maybe the other one yeah, this is better. Takes a while, but it eventually gets to the same point. So these things are tail equivalent. And in general, the point is, right, so something like this is tail equivalent to something like this. All right. Right, so this idea is this is somehow the smallest class of asymptotically equivalent things one could reasonably think of. So what we're going to do is we have this space X, we have our random walk measure on it, and we're just going to keep that same measure, but change the space of a harmonic function, or sorry, change the space of sort of events we're allowed to look at. We're only going to look at tail measurable events. So instead of being able to like talk about any event, we're only going to talk about events that are really asymptotic, that really tell you what's going on, right, from sort of at time infinity, what's going on as the time approaches infinity. So again, the measure is the same, but the sigma algebra is smaller.
There's a question as to whether there's a typo in the definition. I'm not sure.
What's the typo?
Yeah. Konstantin, do you want to just verbalize?
Yeah, so So I mean, you start like what you write like in T equivalence, you write G1, G2, and so on. But I guess you should start at a later point, right?
No, sorry. I want to be very clear here. That was not a typo, but thank you for the question. Right, if you see, because there's two notions of tail equivalence. Thank you for bringing this up. I want my position at right. So I have my two random walks. So one of them, I want my position at time m, and my position at time n. I want them to agree from that point on. So maybe the random walks do something different, but at that point on, they agree. Now, if you look at G1, G1, G2, G1, G2, G3, these are telling me the position. So if I want to know what my position is at times 3, it's G1 times G2 times G3. If we looked at the other notion, this other weaker notion, or I guess stronger notion, no weaker. Yeah, if we look at the other weaker notions, the issue is that by a Kolmogorov 0-1 law, it's always going to have probability 0 or probability 1, which is very nice, but isn't going to tell us anything about when random walks exist. Does that answer the question? Like, we want the random walks, we want their positions to agree from some finite times on.
And maybe just so the measure on the quotient is the push forward.
Yeah, the measure on the quotient is the push forward. Or like the way I think of it is it's the same measure, but we're changing the sigma algebra. But you can think about it as a push forward as well if you prefer. Right, so right, again, why are we doing this? There's this motivation of the world of random walks. This is an incredibly weak notion of asymptotic event. I don't think there's a weaker notion of asymptotic event you could ask for. The one exception I can think of is changing M and N to require them to actually be equal, but it turns out under some very mild hypotheses that notion is going to be equivalent. So really, we're asking what are the possible asymptotic events that a random walk could have, right? And another way of thinking about it, related but slightly different, is we're just trying to quantify all the different asymptotic trajectories a random walk could have, right? There's a lot of asymptotic trajectories, but is there sort of any measurable difference you can tell, or is every single thing sort of part of the homogeneous blob? If any of you have heard of ergodic theory, it's somehow the Poisson boundary being trivial. Well, in a very literal sense, it means the equivalence relation is ergodic. So it's related to these things in dynamical systems where you have things which are mixing, where there's no way to really distinguish any events. And one last interpretation, which I'm going to sort of come back to later, is that E being measurable implies that for every epsilon, there exists an n such that up to an absolute epsilon error in probability, you can tell whether you are in E just by looking at the first n steps of your random walk. So what this means is that for an event E to be measurable, what that's saying is that there's some n, maybe it's 100, maybe it's 1,000, maybe it's 1,000,000, but there's some n where if I just tell you where you are at step 1,000,000 of the walk, you're already going to, up to a very small error, know whether you're in the event or not. So this is somehow what you should think of an event as being. This is essentially one of Littlewood's principles, but it's a good way to think about a measurable set for people who maybe haven't been doing measure theory in a while. And again, the idea associated with this is, what can I learn about where I'm going to be as time approaches infinity, as time is really close to infinity, just by looking where I am at some finite step? Is there anything I can learn? And the answer is, well, sometimes yes, sometimes no. So there's a very natural group action on the Poisson boundary. H acts on X by sending random walks to random walks which start at H. So G1, G1, G2, G1, G2, G3 get sent to H, G1, H, G1, G2. HG2, G3, and so on and so forth. I want to be very clear. This action does not preserve the measure. This is not a measure preserving action, right? So you have sets that get bigger and sets that get smaller. But it's the next best thing. It does preserve the measure class. So if something happens with probability 0, when I shift it, it'll still happen with probability 0. And if something happens with small probability, there's a positive constant multiplier only dependent on h, which says, okay, you're still small, maybe you lose a multiplier dependent on h, but that's all. It turns out these things are actually equivalent. Moreover, and I'm not really going to go into this, it is something called a stationary action, which somehow means that if you take a random element of G chosen from mu, the measure on average is invariant. But I'm not going to go too far into that. Am I getting some questions?
And you said it is mu invariant, right? It is mu, what did you call it? Mu stationary, right? Yeah.
It is mu stationary. Yeah, if I take a random element of G chosen from mu, it's not going to change things. And recall also that there's a natural G action on the space of harmonic functions, just by doing this. And wow, it's two groups acting on two different things. What are we going to do? We should figure out a way to interrelate them. So the main result, and this isn't actually especially bad to prove, I'm going to show sort of the things, but I'm not going to go through all the details, is the following correspondence. So let's call B the space of bounded harmonic functions on G mu. Then B is isomorphic to L infinity of the Poisson boundary of G mu. Furthermore, the isomorphism intertwines the G actions on both spaces. So I have act on G on one space, it's the same as acting on G on the other space. So like they're isomorphic as representations. So what is this saying? This is saying that really all the harmonic functions, you can view them just as functions as, L infinity of this weird measure space. The L infinity is not surprising, right? That's just saying that it's bounded. But it's not at all clear there should be such a measure space. And the measure space comes from random walks, and this is about harmonic functions. This is a really cool correspondence. And surprisingly, it's not at all that bad to prove. But before I talk about this, right, this is a cool object. It has the structure of group isomorphism. It has all these things. But even if you ignore the group isomorphism, even if you look at it at the level of abstract vector spaces, where most of the time these are infinite dimensional and it's not going to tell you anything of interest, it already does in the very special case where the Poisson boundary is trivial. So the Poisson boundary is trivial if and only if there are no non-constant bounded harmonic functions, right? Because if you have a measure space where the only events are 0 and 1, well, L infinity of that is just the real numbers. So the only harmonic functions they're going to get are the real numbers. So how do we actually construct these isomorphisms? This is, I hope, the last time I have to bring up the word Martingale Convergence in this mini course, but the answer is Martingale Convergence. If I have any function like f, or like, right, if I have any harmonic function f, right, I can define, right, a martingale on it, right? So I start running f of my random walk. I take a random walk starting at the identity, and I runs a random walk. And then I apply f to each step of that random walk. So G1, G1, G2, G1, G2, G3 gets sent to f of G1, f of G1, G2, f of G1, G2, G3. And first of all, this is going to converge almost everywhere. That's just a statement of Martingale convergence, that this map is actually going to converge to some real value. The real value it converges to, well, it must obviously be bounded because the harmonic function is bounded. So we're taking a bunch of values of a harmonic function, so it has to satisfy those same bounds. and also tail equivalents of sample paths, tail equivalent sample paths obviously converge to the same value. Why? Well, they're literally the same sequence, except they have a few possibly different entries at the front. But except for finitely many coordinates, we're just literally taking two versions of the same sequence. So of course they converge to the same thing. And to get the map in the other direction, you just compute the value of fg, right? To compute the value of something given an element of L infinity of the Poisson boundary, simply take the expected value of a random walk starting at g. So you take a random walk starting at g, this probability 1, right? It's gonna end up in one of these tail equivalence classes, and then you take the expectation of that. And I should be clear here, we don't actually need a priori. You get a map from just L infinity of the original measure space. This sort of already works if we just have any L infinity function of of your measure space. But if the thing is not tail equivalent, you're going to get a kernel here. So the idea is basically I run my random walk till time infinity and then look at the value of the Poisson boundary and then just average over all my possibilities. And so this gives both directions of the isomorphism. Questions so far? All right. Okay, so I feel like I've gone a very long time talking about harmonic functions or bounded harmonic functions without ever bringing up that these are things that actually exist. I feel like I should argue that at least one bounded harmonic function actually exists. And I should be clear. In the exercises, if any of you decide to compute it, you're going to actually go and compute this harmonic function. It's not so bad. All right. But we're going to look at it first from the point of view of the Poisson boundary. So I'm going to do this on the free group on two generators. And the measure is just going to be a quarter at A, a quarter at A inverse, a quarter at B, and a quarter at B inverse. So I'm just taking a random walk on, really, you don't even need the group structure here, right? It's just a 4 regular tree. I'm starting at the origin, and then I'm just stepping in a random direction at each time. All right. And let's call A the event that the sample path begins with A at all but finitely many coordinates. So for example, if I start with B, but then go to the identity, and then go to A, and then go to AB, and then go to ABB, and then go to ABBA inverse, and then go to ABB, and then go to ABBA, because I have this A here, and this A here, and this A here, and this A here, and I'm going to have A's to infinity, I'm in A. On the other hand, this event, which is sort of a very rare type of event where I start at A, and then I go to the identity, and then I go to B, and then I go to the identity, and then I go to A, and then I go to the identity, and then I go to B, and then I go to the identity. Well, there's infinitely many times where I don't start with A, so I'm not in the event. And similarly, B, BA, BA inverse B, BA inverse BB, I'm going to start with B here, so I'm not going to start with A. So this is a tail event, right? I've said, well, all but finitely many things, you're going to start with A. If I change finitely many things, still all but finitely many things are going to start with A. But we still need one last step, right? We can't just show that there's a tail event. We need to show that it's non-trivial. Well, with probability 1, any sample path will start with the same symbol for all but finitely many elements. And this follows from the law of large numbers. What's going on? I'm going to... Well, ignore the identity for a second. That's a little bit of technical complications, but it's not really the main point. At any point but the identity, right? So if I start here, 3/4 of the time, I will add a symbol, right? If I had an A, a B, or an A inverse here, the length of this word is getting longer. In 1/4 of the time, I will remove a symbol. So by the law of large numbers, as time goes on and on and on, I'm just going to keep on adding symbols. At some point, I'm going to sort of right, the number of symbols I have at time n is going to converge. It's going to grow like n over 2. And what about the identity? Well, at the identity, things are even better. If I start at E, no matter what symbol I add, I'm just going to add a symbol. So the point here is we're actually going to, essentially, almost surely, past some point, things are going to stay basically, the words are going to be basically at length n over 2. But to change symbols, if I want to change symbols, I need to go through the identity. Right? I'm doing this on a tree. If I want to get from A to B, well, I need an A inverse multiplying me down to the identity first. So just the fact that the length is going to grow is going to already imply that almost surely you'll eventually start with one symbol. What did I just do? But by symmetry here, 1/4 of the time I'm going to start with little a, 1/4 I'm going to start with A inverse, 1/4 I'm going to start with B, and 1/4 I'm going to start with B inverse. They're all equally likely, right? It's just which of the 4 directions of the tree I'm going to go on, right? Of course it's symmetric. So this event's going to happen exactly 1/4 of the time. So it's going to give you a non-trivial bounded harmonic function. And we're going to calculate this harmonic function in the exercises if anybody likes. It's a cute calculation. I promise you, it's not too difficult of one. All right. So now I want to talk about sort of the coolest examples in the theory. So these are the so-called Lamplighter groups. So it's Z over 2Z ref ZD. And I'm going to draw a picture very soon. So don't worry if you haven't seen reef products before. But what does this reef product construction mean for people who haven't seen it before? Well, it's going to be the semi-direct product of Z over 2Z to the Z mod D with Z to the D with the homomorphism given by shifting. And I should be clear here, when I say product here, I mean you can have finitely many and it's one everywhere else. I don't mean the weird uncountable group version. That's sometimes also called the Lamplighter, but I'm only talking uncountable groups here. And the idea is you walk on Z to the D and turn on and off lamps at each coordinate. So again, I'm going to just share a picture. So apologies, my lamps are going to be very poorly drawn. But and also I should be clear, this is technically somehow a picture of something the group is acting freely on. This doesn't really matter though. It's how I think I and almost everyone actually think about this group, rather than as some weird thing. And honestly, it's a good way to understand reef products in general. the way you think about reef products is always as some sort of a possibly more complicated variation on this. All right. So you have a dude or a person who's walking around a street. And on that street, there's an infinite array of lights. One to the left, some to the left, and some to the right. And what can this person do? Well, each of these lights, they can turn it on. It can be on or off. So what our lamplighter is going to do is they're going to walk some number of steps, and as they're walking, they can flip the state of a lamp. So they can turn an on lamp on, off, or an off lamp on, or they can just leave the lamp be. So maybe our person is going to go left, turn on the lamp, go left again, and turn on the lamp. Right, so then this lamp would stay the same. This lamp would change. This lamp would also change. And the person would end here. Right, so in general, this person, they move around finitely many steps. They turn on and they turn off lamps. So this is what this is what this person is going to do. And all the different ways you can do this, right? It's easy to compose this. If I go right by 2 and then turn on a lamp, I can easily compose this by going left by 3 and then turning off a lamp. First I go 2, I turn on a lamp, then I go 3 and I turn off a lamp. Or I flip the lamp. I should be clear. I keep on talking about turning on, turning off. That's a misspeak on my part. The lamps, you just pull the lever and it flips the state. There's no notion of on or off, really. There is, but it's a relative thing. So you just flip the state. You can't tell the lamplighter, if it's on, keep it on. If it's off, turn it on. You have to tell them, keep it the same or flip it. But the lamplighter can walk on many different groups, right? So we can do this where the lamplighter is walking on Z. We can do it where the lamplighter is walking on a plane of lamps. So this is Z squared. And we can even do it where the lamplighter, say, has a little helicopter and is doing this on Z cubed. So they're going around, turning on lamps, turning off lamps, walking around and finding things. So this is what the lamplighter does. So these groups are solvable, I should say. This is easy, right? You have a normal subgroup, which is Z1, 2, Z to the Z to the D. And then when you quotient by that, you get Z to the D. All right. So the free group, it's sort of a big group. But the lamplighter groups, these are solvable. They're not huge groups. So let's say I have a measure which is equally supported on the generators of Z cubed and also has some support on the lamp. So some of the time my lamplighter is going to be moving. So most of the time my lamplighter is going to be moving left or right or up or down or forwards or backwards. Some of the 6 cardinal directions, but also with some probability they're going to flip the lamp. This three-dimensional lamplighter with this measure has a non-trivial Poisson boundary. So it has non-trivial bounded harmonic functions, but trying to construct them by hand without this point of view of the Poisson boundary is sort of really hard. This was, I should say, this is an example due to Kaimanovich and Frisch, and for a little bit, I think including tomorrow, I'm going to be focusing on some results from a very important paper of Kaimanovich and Frisch, one of sort of the foundational papers in this field. So why does this have a non-trivial Poisson boundary? What's the event? Well, here's where the sort of visual lamplighter intuition is really going to come to help us. right? Our lamplighter is going on, moving around space, turning on lamps, turning off lamps. But as time goes to infinity, our lamplighter is only going to visit 0 finitely many times. This is because the random walk on z cubed is transient. This is part of why I brought that up yesterday, right? So random walk on z cubed is transient, so our lamplighter will eventually stop visiting the identity. And at that point, whether the lamp is on or off is never going to change again. Right? So we're going to, right? So we're going to ask the question, is the lamp on eventually, sort of at time infinity? Does the lamp eventually get turned on and then stay on forever and ever? It's going to happen some of the time. It's not going to happen others of the time, right? Because it's the last time our lamplighter went to the identity, he turns the lamp off, well, then it's off. Thus, there are non-trivial bounded harmonic functions. And I want to be very clear. We didn't really ever construct a function here. We just found some tail event. All right. So, all right. So in 3 dimensions with this random walk, you have non-trivial harmonic functions. That's very cool. We've done this for a solvable group. Well, first of all, the argument obviously works for z to the 4, for z to the 5, for z to the 6. But what about z squared or z? What about the 1 or 2 dimensional lamplighter group? Like, this argument doesn't work, but maybe it's like that recurrence argument in the beginning. We're just not being, in the beginning of yesterday, we're just not being clever enough. So let's consider the same question on z squared. We take a random walk on z squared, which is you turn on the lamp with some probability, you go left, right, up or down with some probability. Note that because z squared is recurrent, any bounded harmonic function is completely determined by its value at z ref 2z to the z to the d, right? The point is that at some point, our lamplighter is going to return to the origin. And so we can just use, right, we claimed this yesterday, right? So we can look at this recurrent subgroup where the lamplighter stays at the origin and has turned on some lamps, right? So he's done some path, he's turned on some lamps, but then he's returned to the origin. And right, and our harmonic function is going to be determined by the values there. Similarly, we can just run our random walk. We can take our measure and run it until our walker has returned to the origin. And because our original harmonic function is mu harmonic, we can look at this thing where we wait till z squared, which I denote by mu z. I guess I should be a little clear here. By mu z squared, I mean the measure where we wait to run the random walk until we're at the identity. So we wait until we're at the identity, and we're still going to be harmonic when restricted to z mod 2z to the z to the d. This is also one of these lemmas, which I proved yesterday. Right, on a recurrent subgroup, you can wait till you hit it. You'll be harmonic with the measure of, what group elements you had to apply until you hit it, and your value is completely determined on that subgroup. But by kidney, z over 2z to the z to the d, this is constant, right? So what we actually have is it's a constant function on, this abelian part. So it's constant on the whole group because it's entirely determined by the abelian part. So in 2 dimensions, it's completely different than in 3 dimensions. There are no non-trivial bounded harmonic functions. There's something really different going on in 2 and 3 dimensions. This is sort of a weird, bizarre phenomena. And I don't think it's anyone's first guess that would happen. You bring up this family of groups and you ask what happens for this family of groups. No one's going to say, I'm sure there's a cutoff between 2 and 3 dimensions where things change radically. And I want to be very clear. This depends on a very important way on our choice of measure in some sense. it's no longer true for asymmetric measures, right? So if our lamplighter went left 40% of the time and right 60% of the time, just already on a one-dimensional lamplighter, well, then you're no longer going to be recurrent and you're going to be transient. So the first argument is going to apply again. This argument will, however, go through for all symmetric finitely supported measures. It requires a little bit more finesse maybe, but the same idea applies. And instead of actually getting into the next topic, I just want to talk philosophically for a little bit, right? So this is cool from the point of view of harmonic functions. This is a really cool result from the point of view of random walks. What it's saying is that if I take this random walk on the lamplighter, it's a very natural thing to do. Every event I could ask about, any asymptotic event I could ask about, any sort of tail event I could ask about, it's either going to happen or not happen. These are in probability called 0-1 laws. So somehow you actually, every question you could possibly ask, every random walk in some sense is going to look the same, except at a finite step part. There's no measurable question you can ask where the answer for one is going to be yes and the answer for no, the other is going to be no. And again, this just completely changes when you get to 3 dimensions. So there's a very cool thing where recurrence and transience, which is sort of a priori this property just about random walks, it shows up at the group level. And I don't really want to start the next topic with 2 minutes remaining on the clock. So I will happily just stop and I think take questions now.
Okay, let's thank Josh for an enlightening lecture, no pun intended. Any questions? I guess I was curious. So, for example, the Poisson boundary of a free group, is this, I mean, as a measure of space, the same as some measure space? Well, maybe as a measure of space, a lot of these things are the same.
Something I'll talk about. We'll see what I have time for tomorrow. But something which is really cool is that actually, in a lot of cases, you can identify the Poisson boundary. And I should be clear here, somehow, in all the cases where we can identify it, we need to put at least some restriction on the measure. But the restriction can be very weak. So if you're finitely supported or have finite moments or whatever, or even a finite entropy, that's going to be enough. And for the free group, the boundary, we know it's going to just be the hitting measure on the boundary of the free group. So we know exactly what it looks like from that point of view, right? The events are what is your hitting measure on the boundary. And for the lamplighters, I don't know exactly what restrictions you need to put on the measure. That's not too bad. But the boundary ends up being exactly what's the state of lamps at infinity. And someone asked, does this have a generalization which covers Brownian motion? And the answer is yes. The sort of original context for this was Brownian motion. If you do this on a manifold, say, you can still sort of just I believe you can still define the same thing. It requires maybe a little bit more finesse. Certainly for locally compact groups and Lie groups, that was actually the original setting for Furstenberg's original paper. The discrete group case came later. The continuous group setting came first, and you can absolutely do it with Brownian motion.
So you showed that like the free group admits a non-trivial harmonic function.
Yeah.
Which implies that it has a non-trivial Poisson boundary.
Yeah.
Does the same sort of argument show that any group containing a free group should also have a non-trivial harmonic function, or that statement isn't even true.
No, the statement is true, but the argument doesn't work. Like I don't think. I mean, maybe I'm missing something, but I don't think you can use